Yes, so I posted the solutions to the practice problems, and I still haven't gotten the chance to put up the solution to the homework. But I just want to mention a few things on the definitions. I mentioned, I think on the definition, I said be able to find orbits, I believe. Did it say that? Yeah, okay. I just want to be sure. So since I said that on there, again, some of the homework was that way, but since I said on definition, I do want to go over some of these. So here again, remember to find the orbits, you just have to go like 1, 7. And I noticed like some books they put commas here, some books they don't. So it's pretty much up to you. 10. 4, 6, and just be sure I did everything right. 1, 7, 10, 4, 6, 1. Then we'll get back to when you can stop. Then go to 2. If 2 wasn't in here, then use it. If it was in here, go to 3. But it looks like 2 is in here. Excuse me, 2 is not in there, so we'll go ahead and do 2, 9, 5, 8, and that goes back to 2, so we can stop. And then go to 3. Now you can put 3 in or leave it off. If it's a single one, you can leave it off. A lot of people just leave. You may ignore this, and a lot of times they won't put this in if it's just it to itself. They'll just leave out, and then you just know if something's not here, it went to itself. So you can put it in or take it out and leave it off. That's up to you. And then notice here 4 is already taken care of. So, and then go to 5. 5 is here. 6 is here. 7's here. 8's here. 9 is here, and 10's here. So I guess we're done. It looks like it's just those 2 if I didn't goof anything up. Any questions on that? And then also, now, in fact, Rudy pointed out like the workbook, they do the, when they multiply things, they multiply them from left to right. That's really unusual. I now put it on the exam, multiply them from right to left. So if you're multiplying stuff, like on this other one, let's see, where was it? Yeah, over here. So if we have this 1, 2, 3, 4, 4, 1, 3, 2, 1, 2, 3, 4, 3, 1, 4, 2. And so again, if we have to find sigma tau, then And then again, we need to go from right to left. So go in this direction. And so then 1, 2, 3, 4. So start over here, go 1 to 3. And then 3 to 3. Two to 1, 1 to 4. 3 to 4, 4 to 2. And 4 to 2, 2 to 1. That looks right. And then, of course, if you're going to do inverse, let's say if you want to do sigma inverse, you can do this several ways. Usually what I do, I just put 1, 2, 3, 4, and just work backwards here and just say, okay, this 1 goes to 2. Then 2 goes to 4. 3 to 3. And then 4 goes to 1. So just kind of look at the permutation, just go the opposite way. So just look up here. Same thing if you want to do tau inverse. Like this. Again, just go over here. See, go in reverse. 1 goes to 2. 2 goes to 4. 3 goes to 1. And 4 goes to 3. And so for these, just be able to for the permutations, of course, be able to multiply these as well. You know, let's say if you were asked to do tau inverse or sigma inverse times tau, you'd be able to do stuff like that. So you would just put and let's see, tau 1, 2, 3, 4, 3, 1. Oh, yeah, 4, 2. So let's say if you wanted to do that, then you would just use the inverse you got up here and the tau from up here. And then once again, go from right to left. And then that would be 1 to 3, 3 to 3, 2 to 1, 1 to 2, 3 to 4, 4 to 1, 4 to 2, 2 to 4. Any questions on any of that? Okay, good. Yeah, so pretty much if you could, for as far as calculating permutations, just be able to do the orbits, be able to do the inverses, be able to multiply them. Yeah, good. Is there any questions on anything on the exam that one has? Yeah. Mm-hmm. Yeah, let's see. Any particular one or just sort of pick okay. Yeah, so let's say, and a lot of times if something is not an equivalence relation, there are sometimes several ways to show that it's not. So let me pick let me pick one A. So here's the set. X in a real such that X equals 0, and they're considered related. X related to Y, where X Y excuse me, X R Y. I'm messing this all up. X Y is equal to 1. So they're related where X Y is equal to 1. And so again, remember we have reflexive, symmetric, transitive. You could, there's a couple ways you could show that it wasn't. So like for example, let's say for transitive, let's say if you have 5, let's say X equal 5 and Y equals 1/5. And maybe what Z would be equal to 5 as well, huh? Could we, let's see if that would work. So that means that, so if we do XY, that's 5 times 1/5, which is 1. And then YZ would be 1/5 times 5. So they're related, but if you do like say XZ, that would be 5 times 5, which is 25, is not equal to 1, huh? So we'd probably say something like that. So this is not an equivalent relation.
So could you just use like the reflexive thing? Because reflexive just means every like number has to be
Related to itself, right? Yeah,
true thing.
exactly. That's right. That, yeah. In fact, let me, that's a good point. Let me write that down. That you're exactly right. So you could, so this would be one way, or if you use reflexive, like Ben is saying, you could say, like, say, for example, 2 is 2 related to 2? And of course, the answer is no, because like you're saying, 2 times 2 is equal to 4, would not equal to 1. Yep. Yeah, look, usually, not always, but many times, if it's non-equivalent relation, there's more than one way of disproving it. And let me do a couple others here. Let me do one. Oh yeah, let me do a couple of these on the back here. So this one is 1D. It says for a set. So the set is the lines in XY plane. And so this time, X is related to Y if X is parallel to Y. So let's go through reflexive. And so, in other words, I guess, yeah, these are lines. Basically, these represent lines. So the reflexive, the question is X related to X, and of course the answer is yes, because any line is parallel to itself. And symmetric. If X is related to Y, of course, what does that mean? I.e., X parallel to Y. Then, of course, Y is going to be parallel to X. So that one's pretty easy. You know, and how about transitive? So, so again, let me just put this yes. Then transitive, if you have like 3 lines, if X is related to Y, again, if X is parallel to Y, and Y is parallel to Z, then of course we can say that X is parallel to Z, huh? Because it'll be the case, you might have something like this is maybe the line X, this is the line maybe Y, and Z somehow could be anywhere. Those don't look very parallel, but they're supposed to be. So if X is parallel to Y and Y is parallel to Z, then certainly X is going to be parallel to Z. So this is going to be yes. So this is an equivalence relation. And then you could say, let's see, I asked you, I think I asked for like describe how the set's partitioned. So the equivalence classes would be like the lines that are parallel to each other. You can sort of say it like that. Or you could, you could maybe think of it this way, like let's say one set would be lines with slope M1, then another set would be lines with slope M2, etc. Of course, this is going to be infinite because you can have an infinite number of slopes. So you could even maybe say it this way: the equivalence classes would be the lines are parallel to each other, or you could, sort of just say something like this. This would be one set, the set of lines that have slope M1. Another set would be line slope M2, etc. Either way. Any questions on that? And the next one, B. Let's see if they're perpendicular, same thing as the last one, except perpendicular. I call that F. It doesn't look like there's an E here. Set of lines in XY plane. X is related to Y. If X is perpendicular to Y. So what do you think about that one? I see a lot of no's right away, huh? What's the one that goes wrong? Yeah. Yeah, I think the first one you have to, yeah, exactly. Good. Because X can't be perpendicular to X. Because you can't have an X and it can't be perpendicular to stuff. That's an easy one. And then the next one, 1G. So the set is X in the integers. X related to Y means that X squared minus Y squared is even. And of course, this one, the reflexive X related to X, you're saying kind of like X squared minus X squared. That's always going to be even. And next one, if a symmetric, if X is related to Y, is Y related to X? And that's certainly going to be true because if you have two numbers such that X squared minus Y squared is even, then certainly just with a different sign, then Y squared minus X squared is going to be even. So we have two yeses. And transitive. If X squared minus Y squared even, and X and Y squared minus Z squared even is X squared minus Z squared. What is that going to be? And of course that you could even just, I guess you could even just use what you have above, huh? Because you could just say this is going to be equal to I mean, you could just logically say it too, but this is going to be equal to Y squared minus Z squared. In other words, if we added Y squared and subtracted a Y squared, we would get what we have up here. We said this is even and this is even. So that's going to be even. That'd be sort of a more fancy way to say it. Or you can just say if this minus this is even, this minus this is even, this has to be even. Or you could do like like here. Or I guess more formally, like say what I'm trying to say is if you have this, you can say, okay, I'm going to add and subtract Y squared in the middle, and then use what I have above. Again, there's several ways to say this. And then, so actually, so then again, what are the equivalence classes this time? So again, if you square an odd number, you get an odd number, right? So then if you square an even number, you get an even number. So, and then of course, if you subtract, let's say, an odd from an odd, you're going to get an even. So, so what can you think of what the equivalence classes would be? You go ahead.
The odds and even.
Yeah, that looks like that's all it is. Yeah. So the equivalence classes are just the odds and the evens. Those are really just going to be two classes. So, so just all the odds are going to be all related, and then all the evens. Because if two numbers are even, they're going to be related. If two numbers are odd, it's going to be related. Any questions on any of that? Anything else you can think of?
We do C on the part.
Oh, yeah, on the same thing?
Yeah.
Mm-hmm. So let's see this one here. 1C. So we have the set of natural numbers. X related to Y. If X equal NY for some integer N. And so again, for reflexive, they're not really sure yet if this is, maybe this will work. So let's start from the beginning. So is X related to X? And I guess the answer is yes, because we could use N equal 1, huh? And symmetric. So if X is related to Y, then is it true that Y is related to X? So again, let's see, that has to be an integer. So if you have like the case where, so it looks like this is where we're going to have a problem, huh? Because if you take, say, maybe X equal to 6, and let's say Y equal to 2. So those are related because then you could have like what, N equal to 3. So what I'm trying to say is 6 is related to 2 because 6 is equal to 2. Let me write the way I have up 3 times 2, where this was our N. So the question is 2 related to 6? Could we find a natural number like this that'll work? It doesn't look like it, huh? No. Not equivalence.
Would it the N have to be 3 or can it be? I mean, we're checking that. Does it use 3 for the other one or could it?
It could be technically it could be a different one if it could work. So for example, let's say if we had said okay, let's say if we had said they were related, Oh, no, yeah, excuse me, this says some integer. So let's say if instead we had said, instead of for some integer, what if we had said some rational number? Then it could work, huh? Good.
So you can change what.
Yes. Yes, exactly. That's right. That's right. You can change it that year to, yeah, like Emmy said, you can change it. So therefore, let's say, again, this will be a different problem, but suppose over here we said that for some rational n, then see this one could work, couldn't it? Because we could say that 6 is related to 2, again, because that's true. And then we could say 2 was related to 6 because 2 is equal to 6. And so now in this case, if you're allowed to use rational numbers, then we could do 1/3, huh? Like that. So like Emmy said, so in this case here, we used one number, and here we use a different one as long as we can find one in our set. But now in this case, since it was introduced, we couldn't do it. Any questions on that? Anything else that looked interesting? Mm-hmm. Yeah, let's see what we. Oh, yeah, I guess that was some of these ones. Yeah, let me go ahead and start with the first one. I think on the paper itself, I probably didn't have the word prove. I have two different ones. And this is the one that says, which of the following are groups? And let's start. We define 2z by a star b, a plus b. So really, it's just saying that our binary operation is just addition. And so the question is, I remember we have to do the CIIA. If you remember, don't have to remember it that way. That's why I usually remember it. The question is the closed. So if you take so obviously these are even numbers. So so let's take there are a lot of ways to kind of say this. So let A and B be into Z. And when I wrote it up before, I kind of did a lot shorter, but you can do a short way, or you can say, okay, then A, if you want to really be rigorous, you can say A is 2n, B is 2m, and then A plus B is going to be 2n plus 2m. And if you factor out the 2, you're going to get an integer. So it's going to be 2 times the integer. So obviously that's going to be into Z. And do we have an identity? Again, this would be the added identity. And yes. And the inverse, does each one have an inverse? If A is into Z, then negative A is also into Z. because it's just going to be the negative of whatever you have. And a plus negative a is going to be 0. So that's an inverse. So in other words, for any a, the inverse is in the set. And then associative, and usually I don't have to do much about associativity because, but let me just say a plus b plus c is going to be equal to a plus b plus c, mainly because in this case, this is a subset of real numbers. 2z is a subset of real numbers, which are associative. So in other words, if you have like a set of something and you take a few out of that set, if the original set, everything was associative, you're not going to change that because you're not really losing anything. Now, if you take a subset, sometimes you could leave out the identity, or you could leave out an inverse. If you didn't have all the members of the original set, it's possible you took a subset, you could leave those out, and therefore these wouldn't be satisfied. But the original set, if you're just taking some of them, if they were associated, if they were associative in the original set, then even if you leave out some stuff, the ones that you have in the subset are still going to be associative. You're still going to be able to add them in some different ways. And let me do another one here. Say 1b. And so this is on the positive integers. And a times b is equal to ab. And so it's on the positive integers. So let's think about this. It's closed. And let's see. How about an identity? The question is there going to be an identity? Is there going to be something like is there going to be some number that when you multiply, let's say a times that number, you're going to get a back? And it has to be like just one identity that'll work for everything. Is there anything you think that would work in that case? Can't think of anything, huh? Yeah, I don't think this one doesn't have an identity. For example, if you tried, b equal 1, you put like a star b and took a times 1, excuse me, yeah, you would end up getting the square root of a. You wouldn't get a back, right? Because the identity is supposed to be something you multiply it by that value, and you have to get the original back. When they're getting a back, we get the square root, so no. And like I said, matrices, because a lot of you have not had linear algebra, matrices will be on. Oh yeah, definitely be able to do either, be able to do, like for number 3, for say the subgroup test, subring test, or the subfield test. Be able to, let's say, to show something like this. In this case, this was for groups, but let me do that one. So suppose S and T are subgroups of a group G. Prove that S intersection T is a subgroup. So that A and B and ST. Again, like we did before, then and all these work the same way. Since these are subgroups, then we're going to have well, first of all, I probably did this a little bit out of order. So A is in S, A and B is in, this is all messed up. A, let me start this again. I'm sorry. I'll make it a little bit nicer. So you want to prove it. So let say A and B in the intersection. Then what does that mean? That means A and B are in S and A and B are in T, just from this. Then because since S and T are subgroups, then we can say they pass the subgroup test, which says that A B inverse is in S and A B inverse is in T. Then from that, we can say that A B inverse is in the intersection since it's in both of those. And therefore, by the subgroup test, S intersection T is a subgroup. And so be able to do that, like say for a subring, subfield as well. And just to review those that test. Any question on that? And it's always the same form. And this comes up a lot in math. That's why I kind of emphasize this. Oh, by the way, let me just say something. I'll have a few harder ones, but I think the last time I gave you some options. This time what I'm probably gonna do is like curve. I'll curve the exam. I'll have some harder ones. But I'll actually curve it. Mainly. That's it for all R. So what we have in this case, so this is really saying, so therefore, so let's say let X, so let X be in that group, the center. Then what does that mean? That we have to say to ourselves, then for all Y in the ring, we have X, Y equals, and actually, let me take two. Let me call this, let's say X and Z. And then we have this, and we have zy equals yz. So we picked two typical ones, and now say to ourselves, then let's check x minus z question. So we want to see if that's in there. And so what is that going to be? X minus z. And then what we want to do, so let me say it this way, let's check x minus z. You want to see if that's in there. And so let's test it. Let's try see if it commutes. That's supposed, in other words, I'm going to see if I come up and see, and then so let's go through and use what we have up here. Yx minus yz, I just distributed that. And then now, based on what we have up here, we're allowed to switch the order, huh? So we can say this is going to be, I guess I'm using these ones now. This is going to be equal to xy, because that's true. And I can use this zy, because that's true. And then now we can factor it out. Y minus z, excuse me, I'm messing this all up. X minus z times y, like that. If that makes sense. In other words,
Oh, yeah, so then I'm commute.
yeah, exactly, right, exactly. Then do the same thing to check x times z and do y. And you could start on either side. I could have started this one on here and then just showed it. In other words, I could have put the y here first and showed it. Doesn't really matter how you start. And then this is going to be like this. And then according to what we have up here, we can say we're allowed to commute these two, x, y, z. Then according to what we have up here, we can commute these two, x, z, y. So and of course, that's going to be the same as like that. So yeah, so that's kind of how you show it, that if you can show that, in fact, you can take this if you want.
Yeah, thank you. So yeah, so that's the subring. The subring test is you show that it's commutative with the.
Yes, now in this case,
That was subtraction?
yes, the first one, in other words, we have to show, so now in this case, yeah, now in this case, now, because we're trying to show, we needed to show commutativity, because that was what was required to be a member of this set, to be commutative. So whatever kind of characteristic of it, whatever the set is supposed to be, in this case, they were commutative members, so we had to show commutativity when we take the difference. So that's right. We picked two typical values, subtract them, and wouldn't need to show if that was commutative, and multiply two typical ones, show they're commutative. That means that they're in the set. And so so what you have, and that's what you were saying here, you wanted to show that was in C, and because they commuted then, so x minus z is in C, and because this commutes, you could say so xz is in C like this. Therefore, you passed the subring test.
That makes sense. Thank you.
You're welcome. Okay.
So can I take the exam on Friday at the day?
Sure. Yeah. Just come to SEO, SE 110. You'll see a lot of people you don't know in there. I'm giving a dynamics test at the same time. So just come in anytime. Yeah, two's fine. Yeah, see you later, Remy.
Which is an ideal one really quick, like the ideal, or do you have something to do?
Yeah, I can actually take a couple minutes.
Just really quick. I
Yeah.
was on that same page, it's just on the bottom there. I think I need the same page if you want.
Oh, yeah.
So it's just that the bottom one there. Cause I know we did it in class a little bit,
Oh,
but I
yeah.
don't feel like I really.
Oh, yeah. So mainly, Okay, so let's say, yeah, let's say you show it's a subring, show that, then what we want to say is, let X be, let X be in the rationals. And that would be our, and then let's say R be in the reals.
Yeah.
Then we have to show, we have to say is Rx in Q
Mhm.
and is XR in Q. That's kind of what we have to show.
Yeah.
So now you can just say, okay, if you multiply, so if you take R times X and you pick any R from here, now let's see what could go wrong. Now, the only thing is the reals include irrational numbers. And so now in this
Yeah.
case, so if you had like an irrational number times, let's say one, well, the easiest thing would be to say one to show it doesn't work.
Yeah.
And so this is gonna be
That would be in the right.
irrational, right? So that's not gonna be in there, that's right.
That's not.
That's not
it's
it,
not
yeah,
there.
exactly. On the other hand, if you had, say, something like, did I put the other, another one on here? Yeah, actually, so let's say on this next one. For 8, let me just mark these so you have them. And then, so for this one. Under is this, and so you'd have to say to yourself, so let. This one you might actually have, since it's small, we may have to, but let's think, and again, let's call this our. Which is a subring, yeah, so I kind of tell you it's a subring already. And let me just call it S, let this be in, and then let R be in Z10. And this one, we may actually have to check each one. Let me just see here. So, or we can maybe just check a few. So if we took like 1, which is from here, times all of these, we would just get the whole set back. So that's not a problem. That one's okay. What if we took, and now we know that the subring, so if we picked any of the evens, we know automatically they're going to be in there because it's a subring and subrings are closed. So if we multiplied this by 2, we know that and they're going to be in it. So let's try another odd one. So let's try 3. 3 times each of these. Let's say 3 times 0 is going to work. Let's say 3 times 2. What's going to give us 6? And if we took 3 times 4, that's going to give us 12, which mod 10 is going to be 2. And now you probably don't have to check every single one, but you can kind of see how the pattern is going.
Yeah.
That if you pick, you could sort of argue, you could actually try every single one here, but like I said, you could say, okay, if anything's already in the set, we know it's a ring, we know it's closed, so we don't have to check those, and then just check some of the other ones. And you can maybe kind of see a pattern. Or if you wanted to be sure, you could just check all the odd ones.
Yeah.
And then you can see that they're going to end up being something in the set.
Oh.
And then since you asked, let me just do one more. So therefore, so the case of 4Z, once again, if you let X be in 4Z, and then R would be in your original ring, then of course, what's X going to be? That's going to be some integer times 4 for some integer in Z. And then, so if you multiply this, excuse me, I'm sorry, this should be, yeah, this was the original ring, because this was actually the integers was the original one. So if we took an R times X, that's just going to be another integer, huh?
Mhm.
And so that's just going to end up being like, say, M times 4, which is going to be 4m, and then that's gonna be an integer. So that's gonna be in 4z, huh? So no matter what integer we picked here, we're just gonna end up multiplying it. But there's always gonna be a 4 involved.
Yeah.
And since we know the integers commute, we don't have to check XR.
Oh, yeah, because that's why for the other one as well. 'cause
Right.
multiplication.
Exactly, yeah,
Really?
exactly. So these ones, that makes sense for
Yeah,
this, yeah,
yeah.
and that's why this one is yes.
Yeah. And then it's that one, you also say it's a subring there, or because,
Yes, so therefore, you don't have to even check that.
yeah.
So if I tell you it's a subring, you don't have to check that part.
Then if you wouldn't, I would just do subring.
Right, exactly.
Makes
Mhm.
sense. Thank you.
Yes, in fact, let me give these to you. There you go, sir.
Thank you.
You're welcome. So how's everything else going, Owen?